Unit 10. Let's start off on a good note of learning what we need to, okay? So what we're talking about in Unit 10 is, I guess if you're a fan of Marvel, you could think in Unit 10 we're getting quite quantum realm-like. So we're going to be looking back at the atoms. It's been a while since we've talked about the atom actually, because we've just been talking about how they react, but now we're going to get back into the depths of the atom and what it makes up. We're going to better understand in this unit what the electrons in an atom are doing. Because so far all we've talked about is there's these electrons, they're on these rings, and they orbit around. It's important to recognize, this isn't in your notes, these first slides, this is just kind of reminding us. So when we last talked about the atom, it's important to once again recognize the difference. This is often how we draw it, it's how we build it, it's how we think about it, because it's a simple way to think about an atom. But when it comes to the truth of the matter, it's quite wrong. This isn't what an atom looks like. This is actually a better picture, even though it looks more confusing, of what an atom is. That an atom isn't these set tracks that the electrons are stuck on. Right? It's not like a Hot Wheels car that just goes on the same orbit. They do orbit, but it's not as concrete as this looks. So that's what we're going to be actually better understanding is these electrons here. Now, as part of this unit, because it is kind of tricky getting down into the quantum level, I'm going to give you some, they're kind of silly analogies, and that's just how if you haven't learned already, that's kind of how I teach in general, to try to help you connect to it. So try to create this visual, even if it's not perfect, right? I think I told you this quote the first time we learned about atoms, that it's better to have a model that is simple and wrong than sometimes a complicated model that is correct. Because if it's so complicated that you can't grasp it, then what's the point of the model in the first place, okay? So last time we did our little demonstration with our microwave, so kind of get us going. Here's just a little clip to remind you what we kind of discussed.
Never really see that on a menu when you go out to dinner. What's the Caesar salad and the Hot Pocket? Tonight's specials, we have a sea bass, which is broiled, and we have a Hot Pocket, which is cooked in a dirty microwave. And that comes with a side of Pepto. Is your Hot Pocket cold in the middle? It's frozen. But it can be served boiling lava hot. Will it burn my mouth? It'll destroy your mouth. Everything will taste like rubber for a month. All of the Hot Pocket. Hot Pocket!
Okay, so we talked about this idea, right, of with our chocolate bar, how we had some spots melted and some spots not, because it's literally traveling in a wave. And if those waves don't hit certain spots, then they don't heat up. Right? And I think you and Jacob brought up Hot Pockets. I feel like they're like one of the ones that like get you all the time, right? Of like being frozen in one spot, but then boiling hot another. So to help us better understand electrons, we're going to take a little side step today and learn about waves. Because waves play an important role in understanding the behavior of electrons. Okay, so they talked about last time with our nuclear presentation, this idea, this is a demonstration last time, they used the word radiation, right? How that's something people are afraid of when you're dealing with like nuclear power or other things. Now, something I want you to understand though is actually radiation is a very broad group of things. Scientifically, radiation is simply anything that is a form of light. Anything that is a form of light is considered radiation. So technically, I could have a big sign on my door right now that says, warning, radiation inside. And it would be true, because there's lights in here and there's shining radiation on you. Now, obviously, there's dangerous and non-dangerous radiation, but in general, that's what it is. Okay, sorry, I don't know where that little bar won't go away. So the thing about light is light can be considered a wave or a particle, and when it's a particle, we call it a photon. Okay, so a photon is a single packet of light. It's in that box. Yeah?
You're saying we don't even know what light is?
Kinda. We do, but it's like two things at once, right? Now, with this idea, it's a type of energy, and it travels in the form of a wave. So let's talk about the different parts of a wave. You've probably talked about it I think in math classes, so I'm going to talk about the different parts of a wave. But we have the amplitude of a wave, which is the height, so label this on your little diagram. We have the crest of the wave, which is the top part. You have the trough of the wave, which is the bottom part. And then, honestly, the one that we're going to talk about the most is wave length. Okay, which measures from crest to crest, or trough to trough. Same distance. Okay? Now, when we talk about wavelength in this class, we're going to learn how to calculate it today. So with our microwave demonstration, what we could have done, we kind of were short on time, so I rushed it, is we could have taken those two melted spots, gotten a ruler, and if we measured from spot to spot, that would have told us the wavelength of our microwaves. Now, obviously, as they get smaller and smaller, it's not something you can just go and measure. And most of the time, you can't see waves, right? So when we learn how to calculate it, the symbol for wavelength is this Greek symbol right here. Okay, so draw that little symbol, or did I give it to you? Okay, so that little symbol is a symbol for wave, for wavelength. So when you see that symbol, think wavelength. Someone said in my other period, they're like, well, it's kind of like a little wave, if that helps you remember. Someone else said it looks like a giraffe, but I don't know. Okay, you don't need to know this, but fun fact, its name is lambda because Greek symbols have names like delta and stuff. Now the other one we're going to learn how to calculate today is frequency. Okay, frequency symbol it's also a Greek symbol. It looks like a V. It's actually the Greek symbol nu, but that's the symbol for frequency. Now, frequency isn't on our graph because you can't draw it on a 2D non-moving picture. Does anyone know what frequency is or how to describe it? Let's do this, right? I take a guess. Oh, Jacob has a guess.
How often the wavelength passes through a certain point?
Good. So it's all about cycles per second, right? So how many waves, so a cycle is up and down, how many of those per second? Now, it's important to recognize it's not about speed. Frequency is not the speed, because speed is about traveling a distance. What did we say all radiation is? Light. And all light travels at the speed of light. So actually, all types of radiation travel at the same speed, but they do have different amounts of energy because of their wavelengths and frequencies. Okay, another analogy you can think of, okay, because I'm sure you can all imagine this, because you can think of a friend or something. So when you're walking through the hallway today, look for that person right where you'll see that very tall basketball player and his short little girlfriend. Okay, there's always one out there, right? Okay, so think of them as they're walking through the hallway. Okay, so pretend I'm the tall basketball player. Okay, as he's walking, so think of my head as the wave, right? So as he walks, this is like his wavelength. See the wave that I'm creating, right, with my head? Okay, and then his girlfriend who's walking next to him at the same speed, because they're holding hands, right? Her wavelength would be more like this. Okay, so like keep up with his big long steps. So we would say that she has a very short wavelength and a high frequency. He has a long wavelength and a low frequency. My unofficial definition of frequency is how squashed the wave looks. When something has a high frequency, the wave looks squished because it's very tight. Versus a low frequency looks like you've kind of stretched it out. Okay? So as we look at these two things, this is where we're going to learn how to mathematically calculate today. Here's kind of just a picture of our idea of the microwave of why some parts heat and some parts don't. Is these nodes through the wave don't cause heating in the microwave. And so if a point of food stays on that spot, like when we take out the rotating plate, it doesn't get heated. That's why the rotating plate is there to try to help increase those chances. Now this right here is known as the electromagnetic spectrum, and it shows us all the different types of waves there are in the universe. Okay, I want you to label, so there's a box down at the bottom, so label this side is the low energy side of our waves, and this side is our high energy side. Okay, so as we go through the electromagnetic spectrum, we go from low energy, which notice the connection, things with long wavelengths and low frequencies have low energy. That's why radio waves aren't something we're typically worried about when we're talking about bad radiation. Is because they have such low energy they can't really penetrate or hurt us. That's why, like with radio waves, like when you're listening to the radio in the car, what happens if you like go up the canyon? Yes, you lose signal because the radio waves can't penetrate through the mountains. They are too big to get to that point. Okay, and then as we go across, we talked about last time, right, with X-rays. X-rays are getting shorter in wavelength, higher in frequency, higher in energy, and they have enough power to penetrate through us, right? Those waves can literally pass through your body, except for what can't they pass through?
Bones.
The bones, right? And that's why we see the bone picture. As we get down here with gamma rays, these ones are considered the highest energy waves. They are the shortest in wavelength, highest in frequency, right? And gamma rays have some positive things and negative things to them as well. They're so small they can penetrate into your cells. So they're actually used in the treatment of cancer sometimes. They actually can sometimes be so small they can actually penetrate into your DNA, which is the whole idea of how the Hulk was created, is because gamma rays penetrated his DNA and changed his DNA and then he became the Hulk. I'm not saying the Hulk is real, but the science behind it is somewhat true. Okay. A cool thing about gamma rays, so at SU when I was studying there, we did this experiment where we took some strawberries, okay, and we put them in this container and we blasted gamma rays at them. Okay? Now, when you send microwaves through your food, does the microwave stay in your food? No, it just passes through, right? So it's not like you have to be worried like you're going to eat these radioactive strawberries now. What do you think sending the gamma rays through the strawberries did, though? Any thoughts? Say what?
Mutated.
It didn't mutate them.
Did it cook them?
It didn't cook them either, but not that thought.
It made them vibrate.
So as it's sent through, because it's so small, right, is the gamma rays killed all the bacteria in the strawberries. So those strawberries were able to stay fresh for about 2 weeks because we killed all the bacteria that would make them go moldy and stuff like that. So gamma radiation actually a way in which you can preserve food, and I think it was pretty cool to see. Yeah?
Wait, so you said it didn't heat up the strawberry? So why do microwaves heat up things when gamma rays do not?
Good question. So it's all about, so there's a combination of, because they do have high energy, right? But the concentration of them also is what like would cause them to heat up as well. So like the amount that we put in, right, we controlled so it wouldn't cause them to actually heat up. But good question. Any questions on that? Now this is the only section right here that we can actually see. Visible light, the color spectrum, is the only part our eyes can see. What's cool is there's actually some animals that can see in the other spectrums. Does anyone know of some that can?
Butterflies.
I'm guessing, I know bees can. Butterflies probably fall in this category then. So bees and butterflies can see in the ultraviolet spectrum. I'll pull it up later. So what's cool about it is how flowers look to them is quite different. And that's what allows them to like find the pollen and like what they need.
The mantis shrimp.
Oh, where can mantis shrimp see? I don't even know what a mantis shrimp is.
Mantis shrimp has like 17 bones.
Really?
Or we have,
It's a really, like,
it's a really high number. It's like, it's crazy.
Huh.
They have an entire like page that you just like scroll through. It takes like 5 minutes. We should totally look at it.
Of just like all they can see.
They're like it's just search up why mantis shrimps are my favorite animals.
they're on point.
All right, and I'll have to. I have no idea even what a mantis shrimp looks like. So, I heard someone else say another one. Snakes. Yes, snakes can see in infrared, which is in a sense like heat vision. They can actually see in those spectrums. So, okay, so I'm about to change your lives with a song, everybody. Are you ready?
Yes.
Now, with this song, it's just to help you understand the order of the spectrum, okay? And yes, it will definitely probably get stuck in your head. But if you are willing to sing along to the last chorus, so it's kind of, it's like 3 minutes, that's all. But the last chorus, if you sing along, but you can't just lip sing, you have to be singing, then you can have 5 smiley faces. Okay? Okay, this song is the work of genius.
Let me tell you what they are. Radio waves, microwaves, infrared radiation, visible, ultraviolet X-rays, gamma rays. From the TV station to your living room, that is the work of radio waves. Heating food in just seconds. Microwave to that. Heat treatment for illness. Take pictures in the dark. They are even in your remote control. Infrared radiation. The electromagnetic spectrum is just a means of a range of radiation. Let me tell you what they are. Radio waves, microwaves, infrared radiation, visible, ultraviolet X-rays, gamma rays, red, orange, yellow, green, blue, indigo, violet. That is the only kind of spectrum that can be seen by us. Bacteria and viruses used to detect forgery. That is ultraviolet. The electromagnetic spectrum is just a name of a range of radiation. Let me tell you what they are. Radio waves, microwaves, infrared radiation, visible light, ultraviolet X-rays, gamma rays. See your broken bones and your hidden bones. Of X-rays, kill cancer cells and sterilize. Dangerous gamma rays do that. Now we have completed the electromagnetic spectrum. If you still do not understand, then play the song again.
Okay, your cue's coming up. Ready? Pretty much I just want to hear the order. That's what I want to hear.
Let me tell you what they are.
Okay, here goes.
Radio waves, microwaves, infrared radiation, visible light, ultraviolet X-rays, gamma rays.
Work. That was really good. Okay, ready? Let's say the order one more time.
Also worth it.
So it goes.
Radio waves, microwaves,
Infrared, I think I wrote that. Ultraviolet, X-rays,
gamma rays.
Okay, if you settle along, you can give yourself 5 smiles.
Oh yeah.
Okay.
X-rays.
Pretty good stuff though, right? I want to go download it from YouTube.
Yeah.
Don't worry, I'll edit that out of the video I'll post. So, unless you don't want me to.
You don't need to.
So everyone who's
So
absent can
everybody
enjoy
know
your
our
singing.
sins.
You guys did a really good job. Okay, so with this order, let's do this. So without talking to your neighbor. Okay, so on your own now, answer these 5 questions about the spectrum. Okay, so true or false, they're on your notes. Okay, so don't look at your neighbor, just on your own, answer these 5 questions, true or false. You can look at your spectrum to help you. When you're done, set your pencil down. Okay, if you think the answer is true, make a T. If you think the answer is false, make an F. Okay? All right, number 1, radio waves are the longest waves and have the least amount of energy. True or false? Show me your sign, please. Very good. That is true, right? Because they're on the farthest of our spectrum. Okay, number 2, gamma waves are the shortest waves and have the greatest amount of energy. True or false? Also true. Very good. Okay, number 3, radio waves travel more slowly than gamma waves. Hope I tricked some of you. It is false. Why? They all travel at the same speed, right? It's not that they have more speed, it's the energy that's different, right? But they all travel at the same speed. Okay, number 4, red light has more energy than yellow light. I forgot to officially say the order of the rainbow, but everyone knows it's Roy G. Biv, right? So this one, if red light has more energy than yellow light, that is false, because Roy G. Biv is from low to high energy. That's why it's illegal in the U.S. to have anything above a green laser, a laser is literally a very distinct, it's a single wavelength. So red lasers are okay, but you shouldn't shine red lasers in people's eyes because you're literally sending a wave straight into their eyeball, right? Green, has anyone seen a green laser before?
Straight into their eyeball.
So green lasers, what can you do with a green laser?
You can
Heat
things up.
Yeah, you can actually shine them at the sky, right? And point out stars. Well, yeah, that's true too. But
So watch this YouTube channel. This guy had a blue laser. It was I don't know the exact thing, but he was able to he was able to melt, he pointed at it at his garage door, and it started the garage door went white.
so I shouldn't tell you this, but I had a student one time who had a blue laser that he got in China and then brought back here. But he brought it to my class. He was one of my AP students and graduated and then came back and visit. And we could put a balloon on the other side of the room and shine the laser at the balloon and it would pop it. Because it has a lot more heat and energy, so it can melt things and stuff from far away. So, and then you can imagine what a violet laser, right, would be able to do. Oh, last question. So show me your answer number 5. I don't even know what the rest of it says. Red light has longer wavelengths than yellow light. True or false? True, because the lower the energy, the longer the wavelength. Very good. All right, so now let's talk about the math side of all of this. Pull this up. So wavelength and frequency are inversely proportionate. Okay? That means as the wavelength gets longer, the frequency has to get lower. Right? There's no possible way, it's impossible to have a wave with a long wave length and a high frequency. Because as soon as the wave stretches out, the frequency goes down. Okay? So the relationship of this between the two, we have an equation that shows us. So in that box right there, write down this equation. So we have C equals wavelength times frequency. So write that equation in this box. Now I will give you this equation on the test. I don't expect you to memorize equations because in AP Chemistry we don't memorize equations, so why would you guys? But you just need to know how to use it, okay? What this equation tells us, so much again, if you need to label, this is wavelength, this is frequency, C is the value of the speed of light, which always is 3.0 times 10 to the 8th meters per second. So that's how fast light travels. Is it travels this many meters in a second. Yeah.
Wait, so what's the difference between the Greek symbol for wavelength, like that symbol, and the symbol for half-life? It's like, aren't they pretty similar?
The symbol we used for half-life was a T of 1/2.
But isn't there? I feel like there's a symbol. Never mind.
Thinking maybe of another Greek symbol, and it could be used like in another case, like in a math or something. It could be used in a different case, right? Because Greek symbol is just a sign. Okay. All right. So let's look at a problem here. So flip your page over and let's try that first problem.
Wait, the speed of light is a what?
Constant. Thank you.
Now, the thing about this equation, everybody, the trickiest part
It's constant.
is the units. You have to make sure the units match before you plug them in. And that's the hardest part. So the wavelength has to be in meters. So if it's not in meters, we have to get it in meters. And the frequency has to be in hertz, which is per second. So hertz and per second mean the same thing. Okay, one and the same. So let's find what is the wavelength for the radio station 99.5. Right, so when that radio station is broadcasting and sending out waves, how big are those waves?
99.5, right?
So 99.5, so this, like the radio station, that's the frequency. Yeah, so this tells us the frequency of a wave, but it's telling us to it in megahertz. Okay, a megahertz is times 10 to the 6. Now, I'll help you with these conversions as well in terms of like the ones that we don't know, like centimeter and stuff. You should know those ones, but the other ones I'll help you with, okay? So here's our problem. So here's our equation. We know C always, so we have C is 3.0 times 10 to the 8 meters per second. That is always the value of C, at least in this class. Okay? That's going to equal, I'm trying to find wavelength, so leave that as the symbol. I don't know what it is.
Is that an 8 or a 6 by the time?
10 to the 8th.
Oh.
And then we know the frequency that we're trying to look at. It's 99.5. But since that was in megahertz, we're going to add times 10 to the 6 to get it to just hertz. So sometimes we're going to have to change our unit so that it can match. All right, now once you have everything plugged in, now we just use algebra to get our variable by itself. So if I want this alone, what do I have to do? Good, so we're going to divide both sides by 99.5 times 10 to the 6. Now, the other biggest mistake I see made is just calculator issues of not putting that in parentheses. If you don't put in parentheses, you will not get the right answer. Unless you use the EE shortcut, then you don't have to use parentheses. But otherwise, you have to. Okay, so we take 3.0 times 10 to the 8 divided by 99.5 times 10 to the 6. When we plug that into our calculators, you'll get an answer of 3.01. Now, for another smiley face today, don't say it out loud, but think in your head, what would be the unit on this number? So don't say it out loud. But 3.01 what? If I'm finding wavelength, think in your head for a second what the unit should be. Raise your hand if you have an idea of what the unit should be. Okay, on the count of 3, if you think you have an idea, shout it out. Ready? 1, 2, 3. So it should be meters. Yep. Because it's a length of something, and wavelength is always in meters. Okay? If you said meters in your head, you can have a smiley face. And that's our answer right there. Okay? So let's try one that's similar but in reverse. Oh, let's put that in perspective. So what that means, so how big is 3 meters? About? Anyone know how big 3 meters is?
About 3 meter sticks.
It's about 3 meter sticks, yes. Right? I don't know where my meter stick went. But it's also like 9 feet. Right? So the wavelength of that wave that comes from that radio station, it's longer than my arms because I'm not 9 feet tall, almost like 2 of me, almost. Right? That's how big it is from crest to crest of those radio waves. Now, we're not talking at all in this class about the amplitude. So I drew it like this just to show you, but that doesn't mean it's actually like this because that takes into account the amplitude of it. Right, which is a whole different thing that we won't talk about, okay? All right, next problem. What is the frequency of light with a wavelength of 5,000 kilometers? Okay, so same equation as before. So we have C equals wavelength times frequency. We always know the value of C, so we can plug that in. 3.0 times 10 to the 8 meters per second. Now this time I know my wavelength. It's 5,000 kilometers. But it has to be in meters to plug it in here.
Kilometer is 1,000 meters.
Good. So if I have 5,000 kilometers, there's in 1 kilometer,
Oh boy.
there's 1,000 meters. So you can just write it like this really if you wanted to. So the wavelength is going to be 5,000. And then we're going to add for every 0, so 3 more zeros. 5 million meters. And then I'm trying to find frequency, so we leave that as a variable. Now, just like before, we just solve for our unknown. So now we're just going to divide both sides. And we'll end up with wavelength equaling, I forgot to write down this answer. Does anyone have it yet? 16? 60. Sounds about right. Any thoughts on the unit for this answer? What do we say we measure frequency in? Yep. Okay, you actually can write that 2 ways. So you can write it as 60 hertz, or you can write 60 1 over S, because that's what a hertz is. So both of those are acceptable. Question, Jacob?
So it's 3 times 10 to the 8, right?
Uh-huh.
Wait, do you have to write E 10 to the 8, or do you just write E 8?
So if you're using, like the EE shortcut, if you're using that, you just write. So you do 3E8.
Okay, that makes sense.
Because did you do 10, 8?
I did 10 to the 8.
So that would add an extra 0.
Yeah.
Okay, let's try 4 more true or false questions here. Okay, so to answer 7, 8, 9, 10 real quick. Ready, set, go. So answer 7, 8, 9, and 10 on your paper. True or false again. And then we have one last equation to talk about, and then we'll hopefully get our homework done in class. Okay, everybody ready? Okay, show me your sign for number 7. True or false? Light with the highest frequency has the highest energy. True or false? Show me your sign, please. Very good. True is correct. Okay, number 8. Light with the lowest energy has the shortest wavelength. True or false? So low energy would mean long wavelength. So that is false. Good. And then radio waves have shorter wavelengths than X-rays. True or false? Very good. Also false. And in our song, it goes in order of increasing frequency. True. Very good. Okay, so the last equation here is how we can now then calculate the energy of waves. Okay, so in that last box right there, okay, so frequency and energy are directly proportionate. So something with high energy has high frequency, or something with high frequency has high energy. And the equation that relates them is, so energy equals H times frequency. So write this equation in that box right there at the bottom. Okay, so E is for energy. This is our symbol for frequency. And this H value right here, this is known as Planck's constant. Okay, so similar to C, in this other equation, it's always the same value. What scientists have found is they found that energy is separated by this very particular, it's a very small amount. And we'll talk a little bit more about that next time as we talk about electrons jumping inside atoms. So the value for H is H will always equal.
Why can't it be something like easy, like 64? It's gonna be like 0.6 times 10 to the 24th, or like.
Yeah. So 6.626 times 10 to the negative 34. Very, very small number. Okay, the units for H are joules. Have we talked about what joules are again?
I think we all know what joules are. Thank you, ladies.
It's just a form of energy, right?
For 5 more minutes.
Okay, so joules are just a form of energy. So it's energy per second. Okay? Once again, you don't have to memorize this equation. I'll give it to you on the test, but you have to know how to use it. Okay?
You have to memorize like the number.
Nope, so I'll also tell you what H equals, yeah. No, because in AP chemistry you don't have to memorize